Welcome to the presentation Hypergraph Structure for Parallel Integration of Databases into CRM. This research focuses on how hypergraph-based modeling can enhance CRM system by enabling parallel data integration and improving scalability. Today, we will explore theoretical foundation, architectural strategies, and practical implications of this approach. This agenda outlines the flow of our discussion. We begin with the motivation for hypergraph modeling in CRM, continue with the design and implementation of parallel architectures, and conclude with transaction management and future prospects. In modern CRM systems, data originates from various heterogeneous sources such as transactions, marketing campaigns, and support tickets. Traditional graph models are limited to binary relationships, which complicates the representation of complex multidimensional dependencies. Hypergraphs, in contrast, allow modeling of relationships between any number of entities, naturally capturing CRM data clusters. The main objective is to achieve scalable, expressive, and efficient integration. This slide visualizes the fundamental difference between a classical graph and a hypergraph. On the left, we see a traditional graph structure where each edge connects only two vertices. On the right is the hypergraph model where a single hyperedge can group several entities simultaneously. This structure is much better suited to capturing complex CRM relationships. In a hypergraph-based CRM model, each hyperedge reflects a specific unit of business logic, such as a set of customer interactions. These hyperedges may include support tickets, marketing campaigns, or purchase records. Semantic weights can be used to define the significance of each connection. This structure aligns more closely with the nature of CRM data. The diagram on this slide shows the core entities in CRM system: clients, support tickets, transactions, and marketing campaigns. These are linked through action-based relationships. For instance, a client making a purchase or submitting a support request. In hypergraph model, all these objects can be grouped into a single hyperedge representing a cohesive data unit. In our model, a customer and all their interactions are considered a single hyperedge. This clustered representation can be tailored to different application scenarios. It enables client segmentation based on behavioral data. Such an approach naturally fits the modularity of CRM systems. The slide illustrates how we can envision a customer purchase and support request as a polyhedron in hyperspace. Each vertex corresponds to a separate event or entity, and the faces of hyperedge bind them into one logical unit. This visualizes the customer's entire interaction history as a unified structure. Each hyperedge has a unique identifier and associated metadata stored in the database. We use PostgreSQL-based schema to achieve both flexibility and high performance. The model remains compatible with standard SQL system. It allows real-time updates during execution. The entity relationship diagram on this slide represents a structure with hyperedge and vertex tables, where one hyperedge can include many vertices. The table stores not only IDs and categories of hyperedges, but also lists of related entities. This allows formalizing the hypergraph structure within a traditional relational format. Parallel processing in CRM systems enables distributing hyperedges across independent threads. Each thread writes data in isolation, ensuring consistent outcomes. This eliminates conflict during simultaneous database access and reduces total integration time. Such architectures allow us to implement a scalable and efficient processing model. This image illustrates how hyperedges are distributed across threads in a multi-thread environment. The intersection topology visualizes potential conflict zone between threads. This approach allows not only effective load balancing, but also strategic planning for isolation and synchronization. Conflicts arise when hyperedge share vertices and are processed simultaneously by different threads. To minimize them, we use heuristic algorithms such as greedy partitioning and simulated annealing. These techniques reduce interaction points and improve synchronization. As a result, the system can scale without losing performance. The graph shows the speedup achieved through parallel hypergraph processing. It illustrates how increasing thread count affects integration time. This confirms the efficiency of using hypergraph models in multi-thread environment. This slide presents a code snippet implementing multi-thread hyper-edge processing. It shows the use of threads and synchronization mechanisms for safe database writers. The architectures ensure secure updates in PostgreSQL. The system is implemented using PostgreSQL for storage and Python for logic. This design matches the structure of hypergraphs and supports parallel data writing. It remains flexible for future extensions. Hyperedges are formed from files, logs, and external sources. They are processed in parallel and written to the database, and central node synchronizes data with the CRM core. After integration, data becomes available for analytics and visualization. The diagram shows the ETL architecture using hypergraphs in CRM. Data sources feed into the extraction module where hyperedges are formed. Then, data flows through transformation and is integrated into the core system in parallel. The hypergraph model simplifies the representation of relationships in CRM. Parallel processing increases performance but requires attention to data conflicts. Effective load partitioning methods are essential. Future plans include using machine learning for automatic strategy selection. Thank you for attention.